Yeah, hi everyone. Today we have Lalita as our speaker. She's a PhD student from MIT, and she's going to talk about her work, Rate-1 non-interactive arguments for batch MB and applications. So let's welcome her.
Thanks for the introduction, Chase. This is joint work with Rishabh Goyal, and my advisor is Yaltam and Kalai, and for notes, I can nothing. So my project is basically considering the question of efficiently verifiable computation. Suppose that Bob has some computation. We'll here denote that by M and X, M being some Turing machine, X being an input, that he wants to outsource to Alice because Alice either has more computational power or knows some witness for this computation if it's non-deterministic, or basically for some reason Alice has an advantage over Bob, and Bob wants Alice to do this computation. But Bob doesn't want to trust Alice to do it correctly. So Bob is going to ask that Alice can send a certificate that she performed the computation correctly. Of course, there's many applications of this. There's theoretical applications that I'll talk about a lot more in my talk, ways that we can use it to build other theoretical primitives. There's many practical applications, including blockchains and cryptocurrencies. You know, the key words I have to put in my talk, so I put them on the very first slide, so I can just never talk about it again for the rest of the talk. Other applications include cloud computing, basically anything where you want to delegate performance of some task to an untrusted party. We can use efficiently verifiable computation. One thing I'll just note at the beginning, we're not concerned about privacy here. I'm not going to prove any zero knowledge properties. We're not showing hiding of something. There's no secret data here. Really, the question is just that Alice is going to prove to Bob that she's performed this computation correctly. So let me get a little bit more formal. So I'm going to define what's called a SNARG, or renaming Alice and Bob the prover and the verifier, which is slightly less fun, but it will be a little bit more helpful as we continue. So what is a SNARG? Again, basically we want some certificate that Alice or the prover can provide that this computation was performed correctly. Basically a certificate that there exists some witness such that M accepts X with this witness. One thing to note is that we are going to need there to be some honestly generated common reference string, which we'll just assume is put in the sky for both the prover and the verifier to use. Other than the honest generation of this common reference string, really this is a non-interactive scheme. We're not considering here the notion of interactive proofs where we have a lot of back and forth messages between the prover and the verifier. It's really just one message from the prover to the verifier. That's why we use the word certificate. It's basically just one message that the prover can use to prove that this computation was done correctly. The completeness property is pretty much what you would expect. If it's true that M does accept X given this witness in some time t, the prover should be able to generate a short certificate. Here, really, it's important that the size of the certificate is substantially less than t. Why? Well, in the non-deterministic case, it's not necessarily as important, but basically we need there to be some reason for Bob to actually outsource this computation, right? We need to gain something from the fact that the verifier now only has to look at this short certificate as opposed to looking at the entire computation and having to redo it itself. The verifier can actually verify the certificate in time much less than it takes to actually perform the computation. We might also hope for some sort of soundness guarantee. Ideally, we would want that, if X is not in the language, or in other words, if there's no witness such that M will accept X given this witness, it should be impossible to produce a certificate such that the verifier will accept. Unfortunately, this is a notion of statistical soundness or proofs. What we actually achieve in this work is a notion of computational soundness, where we have some efficiency bound on the adversary. So we say that it's impossible for an efficient adversary, in our context, probabilistic polynomial time adversary, to produce a certificate that's cheating. Basically, a certificate for some X, such that there's no witness for M to accept X, but the verifier is still going to accept the proof. This we refer to as a SNARG. There's going to be a lot of acronyms in this talk. I'm just going to warn you now. This is the first one. It stands for succinct because the proof size has to be smaller than T, which is the length of the entire, performing the whole computation. N stands for non-interactive. Like I mentioned, it's just one message from the prover to the verifier, not a back and forth where the verifier is adding more random challenges. And lastly, arg is for argument. Just a distinction here. If you've heard the terms proofs before, I'm going to say proofs to mean, basically this certificate thing. I'll use the word proof, but what I mean is a computationally sound argument, not a statistically sound proof. There will be no statistically sound proofs. Yes, that's not a lie. There's really no statistically sound proofs in this talk, so don't worry when I'm saying proofs. I really just mean the certificate. Are there any questions about this before I go on? Okay, so basically what we've done so far, we defined this notion of a SNARG. This is probably something that you've heard of a lot. There's a long line of work constructing these SNARGs. Basically we've been working on this from, basically for like 20 years plus. Why are we not done? Why are we not, happy with the things that we've done? What is still left to do, basically? A couple of notes. So first, a lot of the constructions I listed on the previous page are constructions in the random oracle model. And these are not provably secure. So I know that, we say stuff about, proofs in the random oracle model or a problem, et cetera, et cetera. They're actually much more of a problem in this context than they are in some other contexts. Why? Because the way that a lot of these SNARG construction works and the way that we end up using a lot of these SNARGs is we're going to basically compose proofs, and you'll see a bunch of examples of this as I continue on in my talk. Essentially, we want to say, like, suppose that we have a bunch of proofs. We now want to, further create proofs where we're going to prove that some other verifier for another proof system would have accepted a proof. So basically we're saying we're going to, provide some proof where the M that I mentioned before, like the machine that we're trying to prove for, is the verifier of another proof system. So if that verifier is using a random oracle, it doesn't actually make sense to define now our next proof system, right? What means that we have to instantiate the random oracle as some concrete hash, SHA-2, whatever, in just the case when we're, trying to define our next proof system. Basically, things get very messy, and it's not even, just a random oracle proof. It's actually worse than that. We have a mix of like random oracle proof plus use of concrete hash. There's a lot of reasons why we're really not happy with the use of random oracles, specifically for these proof system constructions. Secondly, a lot of them are based on non-standard knowledge assumptions. Things are not well studied by mathematicians and haven't been around as long. What do we really want? We want constructions which we can prove secure, and we want them to be under well-founded assumptions, especially LWE, our favorite assumption, which is plausibly post-quantum secure. We don't have a break yet, as we do for many other assumptions. Basically, this is the reason why something like LWE gives us a really strong mathematical foundation, and we can have a lot of certainty that this problem is actually hard, even hopefully for quantum computers. So again, what is the open questions and what do we have and what don't we have? So SNARG constructions under LWE, so I'll kind of take out from that huge list I showed earlier, just the ones that are, kind of directly leading up to this work. We do not have a SNARG for NP at all. All SNARGs for general NP languages require, random oracles or non-standard knowledge assumption or something. There are, many like restricted classes that we have some SNARGs for, but really the holy grail is a SNARG for general NP languages from just LWE, which we take, a pretty substantial step towards in this work. To give a little background on previous work, so one of the main works I'll talk about a couple of times during this talk is by Charlie, Jane, and Jin, Fox 2021. If you've seen, they had published twice. This is CJJ21B, if you're curious. But basically, they've created SNARGs for P from using LWE in this work. And related work by Kalai, Vaikunjanathan, and Zhang, and also in 2021, built SNARGs for another restricted class, NTISP, also known as non-deterministic bounded time and space computations. One thing to note is that both of these constructions actually use as a building block SNARGs for batch NP. What is a SNARG for batch NP? I hope you're wondering. They're also called BARGs, so more acronyms. You can keep a running count of how many I get up to during this talk. So again, we have a very similar setup, except instead of just having one instance and one witness, we have K instances and K witnesses, and we want to prove the correctness of all K of these computations at once. As before, we have some common reference string that's in the sky. Completeness is very similar. Basically, if all the statements are true, we should be able to produce some proof. The size bound here, I'll just note that a trivial construction of this, if we have no succinctness bound, just send the key witnesses, right? Obviously that, you can, then the verifier can read them. The reason why this is not trivial is because we actually want to have some gain, right? We want the certificate to be smaller than just trivially sending all key witnesses. And we want a semi-adaptive soundness. This looks complicated, but it's really not. Basically, we want that for any index I star is chosen before the CRS is generated. So it's gonna be for any I star, the adversary can choose I star. Then the CRS is generated. The adversary gets the CRS for I star and basically has to produce some cheating proof, which is cheating specifically on the I star instance. So in instance X sub I star is not actually in the language, and the prover has to cheat on that specific I star. The reason we call it semi-adaptive is because the adversary chooses I star, then gets the CRS, and then basically it's that's why it's not fully adaptive. This is a non-interactive batch argument. The person who first came up with these acronyms just decided we didn't need an N in this one, I guess. So this is just batch argument, but it's still non-interactive. The N is just not an acronym. All right, so this is BARGs, and it's going to be the topic of a lot of this talk. I'm basically slowly going to try to explain all the parts of my title. So we've gotten, halfway there. We've explained one of the complicated acronyms. Oh, yes.
I star is like, there's a different CRS for all of them, or?
No, so basically we choose some I star before we initiate the protocol. And then the CRS is generated in terms of that I star. So yeah, this is a little bit confusing. In the honest execution of this protocol, it doesn't actually matter. We can just basically choose I star equals 1 and generate a CRS.
So the I star, I guess, is the string, the witness you want to kind of break.
Right. So basically, later we'll see a notion of extractability that we can get from this. I star is a witness that we want to be able to extract, but the CRS will hide I star. And so in the proof, basically what we do is we keep moving I star around and we do like various shenanigans in order to kind of reach our contradictions.
Sorry, I'm still missing the point. So in the honest scheme, there's only one.
There's always only one common reference string. Yeah.
So in the honest scheme, it's not indexed by I star.
In the honest scheme, so that, yeah, maybe the notation is confusing. It's not actually indexed by I star. This is just saying that I star was like chosen before the CRS was generated, and CRS was generated for a specific I star, like only one CRS for the any instance of the protocol.
Is it I star that's fixed or XI? So I'm just wondering.
I star, not XI star.
So they don't see the X's. They just.
The adversary gets to choose the X's.
I see.
Yes, the adversary gets to produce the instances X1 through XK that they want to cheat on, including the instance X sub I star. They just have to pick which instance they're going to cheat on beforehand. Basically, yeah, when we're actually using this scheme, we would just, we would basically just pick I star equals 1 and generate whatever. The point is that in the proof, this allows us to, basically like get around, like basically be cheating adversaries by moving around the I star in a way that the adversary can't see, and then being able to.
Let's ignore the I star.
Yes, you can just ignore it. Yeah.
Is it obvious that say you can't get like some sort of adaptive soundness, or you don't get to choose which one? Like it's like if you break one of them, you're the adversary wins.
It's not obvious. There's some like limited negative results, but the kind of techniques that are used in like this line of work, I think it's very non-obvious how to achieve that kind of soundness just because of the constructions. But it's definitely like we don't have like full lower bound saying that we can't. Yeah.
Yes. Going back to your dream about getting snarks from LFE, I was concerned about the specific notion of soundness you considered there, because I believe adaptive soundness is already like generates already rules it out, right, from any standard function.
Yes, so there's again limited negative results in the case of SNARGs for general NP. We can basically hope for a SNARG for a general NP language that has some sort of restricted soundness condition. Even with that negative result, there's still a lot of room for us to kind of be able to build a more general purpose SNARG construction that like would actually have like good soundness guarantees. And we're also seeing a lot of applications of kind of the progress that we've made, even of not full-fledged SNARGs for NP, but something like this, which is quite close and has a lot more power than the SNARGs and BARGs that had existed before.
Just to understand correctly, so the notion of soundness you achieve is not the fully adaptive notion.
No, it's a semi-adaptive notion.
So how would it translate? So I understand the semi-adaptive notion for BARGs. How would it translate in the word of SNARGs?
SNARGs, there's no like the adaptivity. There's not the adaptivity here is because of the choosing of the index.
Right.
Versus in SNARGs, there's no like index to choose.
I guess it has to be a batch. So the adaptive is the index you break depends on the CRS.
Right, but in SNARGs, I think there is the notion of adaptive soundness is you fix the CRS. The adversary gets to choose the statement after viewing the CRS. That's the adaptive notion. The non-adaptive would be the adversary fixes the statement and then it gets a CRS. So I was just asking which of the two notions are they considering?
So yeah, so I guess in the context of like the prior works, like CJJ and KVZ, they get an adaptive SNARG where the adversary can produce the X after the
so basically,
CRS
if K
generated.
is equal to 1, it becomes the adaptive notion for single instance.
Right, but I think that's already ruled out by gender based in my understanding. But I may be missing something.
I guess he's asking about the gentry and mixed lower bound.
Yeah, the gentry and mixed lower bound like rules out a certain notion of like a full-fledged SNARG for like a general NP language. So you're asking like, does that rule out like this result or like prior results or future results or?
Yeah, can you comment on the relationship of that with this notion of that lower bound, right? In this second, because K
Not to a semi-adaptive sound BARG.
But
There, it only applies to like a fully adaptive sound SNARG.
K equal to 1. K equal to 1 is a special case of your population, right?
Yeah. Well, sort of, I mean, in the case of K equals 1, there's like other, I guess it depends on, I will go through a couple of different like succinctness requirements here, but yes, sure, yeah.
I guess is K something that needs to grow with some security parameter or something?
So in general, I'm ignoring a lot of factors that are like log in K, but we will, in most of our applications, actually, we can even just use K equals 2 for like, yeah. It's just,
Are you saying if K is equal to 1, it's subject to that law, but if K is not equal to 1, it's not? I don't understand the relationship. That's what you're mentioning.
right, so the Gentry-Wicks lower bound on a, yes, so I think, yes, in the case of K equals 1, this is subject to the fully adaptive lower bound from Gentry-Wicks, yes. But what we build, we still manage to show a lot of applications from.
So your construction doesn't work like K.
It works in like for everything I've defined here. Like I'm only talking about semi-adaptive soundness.
But when K equals 1, there's no say, there's only one instance, the semi-adaptive goes away, right? It becomes just fully adaptive stuff.
Oh, sorry, so you're saying, yeah. So in the case of K equals 1, yeah, I mean, in that case, I think that then we would, sure, I guess we could, let me define saying like we're going to require K to be greater than 1, like if we're going to use a BARG. In reality, basically, like the way that things would actually work is that we would just, like the construction would kind of devolve to like one of the previous constructions that I mentioned, the CCJJ.
Bargs and SNARGs are different, right? Bargs don't need to be succinct. Like, you just care about succinctness in terms of K, but not in terms of, the proofs could be as long as a single witness, right? So that's the difference, and hence the lower bounds do not apply to Bargs.
Oh, that makes sense.
Right.
Yeah, so I think I'm gonna get a lot more into like kind of the various succinctness bounds of what I want from my BARGs later, but I think that yes, I agree that basically in the case of K equals 1, I think basically then this becomes not a SNARG, right? Because it's allowed to have a full length of the witness. Exactly. Yes. Yeah. Is there other questions or?
I can take it offline later.
There's a question in chat.
Oh. Oh yeah. No, sorry, I'm just reading. I'm parsing. But should I read it out loud for like the recording? Okay. So the question is, I think it's wouldn't adaptive BARGs imply adaptive SNARGs for P. All recent works on SNARGs for P suffer from this limitation, right? I non-fully adaptive. Yes. So the recent works from SNARGs for P do suffer from this limitation. Adaptive, I think so. Is the question fully adaptive BARGs or semi-adaptive BARGs? I think fully adaptive BARGs, yes, do imply adaptive SNARGs for P. Semi-adaptive BARGs do not imply fully adaptive SNARGs for P. Okay. Are there other questions? Okay. So yes, talking about BARGs. So as one thing, as we've kind of been talking about a little bit, one thing that you can do with BARGs is you can compile them into SNARGs. And these two recent results, SNARGs for P from LWE and SNARGs for NTISP from LWE, both work by compiling BARGs into their final SNARG constructions. And there's a couple of lines of other work, even works on statistical proofs also do the same technique. But as I'm about to show, we can also directly use BARGs in a couple of different applications. Specifically, the ones I'll talk about are aggregate signatures and incrementally verifiable computation. But there's a broad range of other ones that have yet to be explored, and some also that we can just immediately plug in our Rate-1 BARG and get applications with better parameters. Let me start by talking about aggregate signatures. So an aggregate signature scheme, first defined in 2003, allows you to publicly and verifiably compress a list of some arbitrary amount of signatures. So in this case, again, just we'll consider it to be K. We have some signatures sigma 1 through sigma K with associated verification keys and messages VK1 through VKK and M1 through MK. What we want is to be able to compress the signatures to some aggregate signature sigma bar. We want that this length does not grow with K. Again, basically, throughout this talk, I'm ignoring log factors, that the length will grow with log K, but it's not growing linearly with K. How do we do this? This kind of very inherently looks like a BARG problem. And so the answer is really just, sigma bar is going to be a BARG that sigma 1 through sigma K exist. This setup is pretty much exactly what we want, because we're not worried about compressing the messages. In most applications, we actually need to keep the messages that's important data. We just want to be able to continually sign something without having the signature grow as the messages grow in length as well. Previously, there's one construction of aggregate signatures under IO and the RSA assumption, but all other ones use either bilinear maps or other non-standard knowledge assumptions in the random oracle model. And this is just for simply, we're just talking about like aggregate signatures, where you're just taking, a set of like regular signatures and aggregating them once into some aggregate signature sigma bar. But as it turns out, in like a lot of actual applications of aggregate signatures, for example, in like many distributed internet applications like BGP route authentication and things like that, what we really want to do is do this multiple times. So what we want is that we can have some, aggregate signature sigma bar 1, and then we can take another aggregate signature sigma bar prime 1 and aggregate those together again. We want to just basically continually do this, like pretty much as much as we want. Of course, I'm assuming that for some of you, there's some alarm bells going off. What is the length of, the sigma bar going to be as we keep popping up, right? The problem that we'll encounter with any previous work, including CJJ, is that if the length of the proof has a multiplicative overhead in the length of a witness, so in this case, the length of a proof for CJJ is the length of one witness times poly lambda bits. This is actually going to have, you can only do a constant number of hops, right? And if you play with the parameters, you can get to slightly super constant, but basically you're going to be limited in how many times you can hop. Versus in our work, we achieve length of one witness with an additive poly lambda factor in terms of the length of the proof, which allows us to continually hop for much more, and we can actually get unbounded aggregate signatures in a multi-hop setting. This is what we refer to as our rate-1 property, which is basically that the proof has rate-1, and that it's basically essentially just the length of a witness plus a poly lambda factor. Yes.
Why is there's no dependence on K?
I'm just ignoring it. There's dependence on log K.
Oh, there's a log.
Yes, yeah. There's a lot of logs that are missing throughout this talk, but yeah, please. There's a bunch of other places where I'm kind of glossing over things, so please ask if it's unclear, and I'll just clarify. That it's basically, yeah, poly lambda log K, actually also like log N, where N is a log of X, and a bunch of other logs actually get thrown in there, depending on because sometimes those things don't overwhelm each other. Sorry, yeah, and it's just the length of X, but yeah, I'm not going into that. Basically, like everything else that's dependent in terms of the additive factor is just like a log dependence, which we'll pretend is like we'll just say like everything is less than like 2 to the lambda, so that all is included in poly lambda anyway. What we really want to think about is just the proof length being just the length of a witness plus some small amount. We actually need another property in order to get all of our applications and to be able to prove security, which is that we need extractability. So what we need is that we are able to, from this rate-1 proof, actually extract the witness WI star. Again, I star was chosen before we generated the CRS, and this extraction happens using a trapdoor that was also generated along with the CRS at that time. And this we call the notion of summary extractability, and I'll put a SE dash in front when we're referring to SE BARGs. Our construction has both of these properties, and we do actually need both of them for our applications. Basically, in like security proofs, you need to be able to actually, reach a contradiction. You need to be able to extract down in the tree, basically, as we're going. For example, here, if you want to, for example, like the actual signature, basically, you have some contradiction, which is that like one of the signatures was actually fake. In order to retrieve it, you need to be able to extract all the way down the tree, which is why we need this summary extractability property. Because of our rate-1 property, we also will have that the sigma bars are not actually growing too much. We are only adding an additive factor with each hop, which means that we can basically continue on hopping as we want. So our next application is incrementally verifiable computation, a really beautiful notion which was first introduced by Valiant in 2008. Basically, you should think of this as an updatable SNARG. So usually we think of a SNARG as being, we have some long computation, and I'm going to sit down and just work out a whole proof that this computation is correct. But that may take me a long time. It's obviously going to take me at least time t, or whatever. Basically, maybe I don't want to do that. Maybe what I want to do is just sit down and do just a little bit of it, just until time t1. And then I'll hand off just like the configuration and some short proof that I've remembered to Surya, who can finish, work until time t2. We keep going on. We just keep handing it off. In a distributed way, we can construct this final SNARG. And all we needed to remember in the middle was succinct proofs. So basically, in this picture, all of these pink proofs are succinct. And we don't need to remember any other information as we're continually going on and updating our SNARG. You really want to think about here, big T as being much bigger than, like, imagine a small space computation. that's going on for a long time, we can do then, this is really helping us to be able to only save, the configuration and a succinct proof, as opposed to having to save a lot more information in order to like continue on doing our SNARG. Previously, this was only known for fixed polynomial time computations under bilinear map assumption. That's the work of Kalai, Paneth, and Yang. By fixed polynomial time, I just mean that you had to like fix some polynomial before generating the CRS. But basically, you can think of this as like we had IVC just for P under bilinear maps before. And for beyond P, we needed non-standard knowledge assumptions or to use a random oracle model. And our construction managed to get for P and for also arbitrary deterministic computations beyond P, again, just assuming LWE. I'm not going to get too much into construction. It's similar to the aggregate signatures, but it gets slightly more complicated because we actually care about having, we care about noting for each block of proofs, like which time sets it corresponds to, which kind of complicates things.
Do you want to adjust the camera?
Oh,
Yes.
Is it like, is that better?
Yeah.
Okay. Great. Any questions about IVC or aggregate signatures? Okay, let me just recap everything I've talked about so far. So in this work, we construct a rate-1 summer extractable BARG for NP from LWE. That's our main theorem statement. And we also show two corollaries. Corollary 1 being that there exists multi-hop aggregate signatures under LWE, and corollary 2 being that there exists an IVC scheme under LWE. So that was basically a full introduction and kind of some motivation for why we actually care about this result. And I'm going to spend the rest of the talk talking about our actual main theorem and the various building blocks that go into proving our main results. I will have to do quite a bit of oversimplification. So again, please just ask if something is unclear, and I'll try to be honest about when I'm lying, even when I do have to lie.
So this is the first IVC scheme.
Yes, so IVC schemes before were known under bilinear maps or random oracle model or non-standard knowledge assumptions.
So this is a very, I would say, a very big claim.
Thank you.
So just to clarify, so there's no SNARG construction.
No. Well, yeah. So let me just give a bit of a roadmap for our main result and talk you through the ingredients that go into our central theorem. So firstly, we have, as I described, a summer extractable BARG with this multiplicative overhead in the witness length. So this can just be like from CJJ. Next, what I'll define and spend a lot of time on is this Rate-1 Flex Hash. This is an intermediate primitive that we define and construct, which we spend a lot of time on because we think it has independent interest outside of this application to Rate-1 BARGs. Actually, a recent work by Kalai, Lombardi, and Vaikunthanathan showed another application of this flex hash, not necessarily even being Rate-1, just a flex hash they used to boost BARGs, basically taking BARGs with like any non-trivial succinctness you can make into like a BARG as good as CJJ using this flex hash. So there's a lot of reasons to think of it as a pretty helpful primitive. And lastly, we'll use a RAM SNARG, which I'm gonna like table until talking about later in the talk. Those two pieces are less interesting. They just come basically from CJJ. The flex hash is the thing that we actually build in this work. And then we also, putting them all together in the central theorem is also another main contribution of our work, because it's pretty non-trivial, even given these three ingredients, how you put them together to get your Rate-1 BARG. So now I'm going to focus on the Rate-1 flex hash. Then we'll kind of zoom out again and talk through the theorem and how we actually construct our Rate-1 BARG. Flex stands for, I came up with this yesterday, so I'm pretty proud of this acronym, a Rate-1 fully local summer extractable hash family. So some of these words might be familiar. I'll talk through what they all exactly mean. So what is a Rate-1 flex hash? So we have some common reference string in the sky that was chosen after some extractable indices I star. We want that the CRS is going to hide what these indices are, but it's chosen like after, the CRS is generated after these indices are chosen. So suppose we have some string X that we want to hash, and we want the hash to be extractable on some certain indices I star. What does this look like? We have some hash algorithm that produces a hash value H, and then we have some extraction algorithm, which given a trapdoor that was generated at the same time as the CRS, can extract exactly the values that were statistically bound, or the values at the extractable indices from X. This is a summer extractability property. If you've heard of a summer extractable hash or SSB hash, that's what this is so far. We have a couple of more things we want. Firstly, we want Rate-1. This is pretty simple. It's pretty much the exact same as the Rate-1 we want from our BARG, which is that we want the hash value to have length, the length of I star plus poly lambda bits. Again, ignoring here, log in the length of X and et cetera parameters, but basically we want H to be the number of statistically bound indices and just an additive factor on top of that. Then we have some more complicated things we want about the fully local openings. So what do I mean by this? We want to be able to open any bit of X to a succinct opening that's only poly lambda bits long. And then we want to be able to verify this opening without even reading the hash value H, which seems kind of crazy. But what we're going to do is verify the opening row against a succinct digest of H. Here, throughout this talk, whenever I say digest, you should just think of, some like collision resistant hash. Really, I think imagining a Merkle tree is the most helpful because all known constructions are kind of what we're going to use this for later, use a Merkle tree hash as their digest, but basically just like some succinct hash that doesn't have any, like extractability properties or whatever. This is going to be our fully local opening property. So if you've heard of local openings, many things like a Merkle hash, et cetera, have a local opening property, which is that, just the first part, that you can produce an opening that's short for one bit. But what we want is that, like, not only is this opening short, not only does it not depend on the length of I star at all, this should be like the size of the opening should be poly lambda regardless of the length of I star. And also it can be verified against just the digest of H and not the full hash value H itself, which means that the verify is actually only looking at things that are poly lambda bits long. Verify, the entire computation that verify doesn't have any dependence on the length of I star. And that becomes very crucial for us in our actual construction of the BARG later. Is the definition clear? Okay, so construction.
Is the digest constructed in addition to the flux and
okay.
the clear?
Yes, so here we can assume, basically just assume that we have some like corresponding, I didn't write it here, so just suppose we have a digest algorithm that takes H and creates digest H. We're only going to say anything about verify when verify is given an honest digest. And then we do a lot of work in our proof, basically when we're using this Rate-1 hash to construct our BARG, we do a lot of work to actually check that the digest was computed correctly. But yes, verify only has soundness or whatever guarantees if digest H was computed correctly, basically by just digesting the hash value H.
I guess I'm confused about the syntax. Does the extractor have any other input like just the hash?
Yes, it has a trapdoor.
And what about open?
Open basically takes in the whole value X. Open gets the whole value X and produces an opening for one bit, which is functionally also giving it H because H hash is deterministic. So open could just recompute hash if it wanted to.
Open takes the bigger hash and outputs row and digest of H.
Yeah, so open doesn't need to output the digest. It could, but basically the digest is just H just getting hashed down by some collision resistant short hash. And then the opening is just getting verified against that digest. So instead of saying verify takes in H and the opening row and the index and the bit or whatever, verify just takes in the digest of H, the opening row, and index and a bit. So everything it takes in is short.
What is row?
Row is just the local opening for one bit of the hash.
What is local?
So basically, we just want to say that row should basically prove the value of some bit originally from X. So we open, so X was hashed down to some value H, and then we want to open the original value of X. So basically, suppose that we want to open this bit of X of sub 15, we want to say is blue. So then this row is basically going to be some sort of proof that X sub 15 was blue. And we want it to be short, no matter what the length of I star was. And we'll see as we're kind of walking through the construction how this is really the hard part. And I think that people are it's good that people are zoning in on this. This is really the technical novelty of the construction of our flex hash is figuring out how do we make this opening local and have all these properties where verify doesn't even get to look at the whole hash value, and then we still want to have that soundness and et cetera that we'll kind of talk about. But well, hopefully I have time.
So the common reference link depends on I star. Oh, I star is the indices that you
Correct.
want to be able to extract.
Yes, but they should be hidden, given the common reference string should not reveal I star.
But it depends on us.
Yes. So let me get to the construction because I think that that'll become a little bit clearer how that works. A construction. So let's assume we have some FHE scheme. I'm just going to say we really need actually a little bit less than that, but basically just assume we have some FHE scheme with an encryption algorithm, a decryption algorithm, and some evaluation algorithm. This basically means that we can just evaluate functions of our plain text while given only ciphertexts. So how are we going to actually construct this flex hash? The common reference string is going to be an encryption of the extractable indices I star, which hides I star by semantic security of our encryption scheme. And the hash algorithm is going to evaluate the selector function. So basically just, this is getting a little bit, if the notation is not clear, basically the point is that we're going to evaluate selecting out those indices I star out of X, but do it using FHE. So we're going to evaluate the selector function is defined by the encryption of X, and then we evaluate it on the CRS, which is the ciphertext, which is an encryption of I star. So yeah, let me just go a little bit slowly here because I think it's not necessarily clear. Eval is taking in CRS, which is a ciphertext, and then, oh wait, you can't see what I'm doing. Okay, yeah. CRS, which is a ciphertext, and eval, which is, eval is the FHE evaluation. Cell is the function that's getting evaluated, and it is defined by the encryption of X. I don't think I'll have too much time to go into like how the construction of this actually works, but basically just like the thing to note here is that we're homomorphically evaluating in order to basically get, what do we want? We want that H is exactly an encryption of the extracted bits that we want, right? Because that's the property that FHE is giving us. The selector function is just choosing those bits, which means that if we decrypt H, we get exactly what we want, which is the original values of X. This is summary extractability. Does this construction make sense? I don't think I'll have time to go through the,
Where is this indices encoded
in the CRS is an encryption of the indices.
Oh, okay.
I didn't want to clutter. In reality, if it's bothering you and you're like worried about it, the public key is actually in the CRS, and then the extraction is also using the secret key to decrypt. But I thought like this is the bare bones of kind of what's actually happening in the construction. The CRS is an encryption of the indices you want to save. Then the hash algorithm just homomorphically evaluates on this ciphertext so that we save exactly the indices we want, and then we can decrypt to recover them.
Maybe this will help conceptually. Why do you need FHE here? Like what is being homomorphically evaluated?
The function, the selector function. Oh, so basically, like hash takes in the CRS, which is an encryption of the indices I star, and X. And basically what it outputs is an encryption of like X on all those indices. Because the function selector basically takes a string and then selects out exactly the indices of the. So select is basically like, the reason why it maybe looks a little bit confusing is because select is defined in terms of a ciphertext and then has to like decrypt that ciphertext in order. But basically here, like X is getting encrypted and then decrypted again inside the homomorphic evaluation. I think the thing to understand probably is that H is an encryption of like X sub I for I and I star. Is I think the thing to take away here, if that makes sense.
So when you compute the hash function, that selection function is computed with respect to that capital I star.
So select, yeah. So basically, what's actually going in there is like our I star, because we like eval is going to take this as input and this as the function. So we are like end up like run like basically what the output of it is the output of selection on like CRS as the input to selector function and X used to define the selector function. This is basically because it's actually like insecure to do it the other way around might be more like intuitive of, defining that we can define the selector function by the I star, right? And then, you put in the X and as input. It just turns out that doesn't work because basically like you can't prove it secure because of things. So this is the construction block. Yeah, basically just remember that H is an encryption of X sub I for I and I star. I'm going to skip through the construction. Basically, like it's a tree, and that helps us because trees are local, and so we need this local property later. But basically, so what are we going to do? Everything I showed is only like actually helping us for one index. Oh wait, sorry. Basically, we're going to. What we have so far is not rate-1, right? Because we're encrypting all these ciphertexts. What we have at the end is like an encryption of m bits, but it's going to be length m times however long the encryption. Each encryption is.
There's a question in chat. Is extract also generating digest?
Extract also generating digest. No, so here extract is just basically taking an H and using the secret key to recover the bits that we want to extract. The digest, I haven't actually gotten to at all describing the openings here. So we can just imagine that, I mean, I'll talk about it a little bit later, hopefully, but basically we should just imagine that the digest is computed honestly, and then, you know, like later on, we're going to check, like we assume it's honestly generated for now, and then we actually check it, you know, when we use this this flex hash construction to build our BARG later.
So the Merkle tree is a digest of FHE ciphertext. Like if you commit to it and since FHE value is deterministic, this is enough.
That's kind of the idea. It turns out it gets a little bit more complicated. We really need these like properties. Like we can't even actually use like an existing Rate-1 FHE. We have to kind of modify the way that the Rate-1 compresses ciphertexts in order to do it in a more local way. So basically that we need to have the property that as we're doing this hash, we're never really like taking, you know, we're never computing a bit based on too many bits from the previous step in order to create our local opening later. But I think, yeah, so the construction is pretty much very similar to what's called an SSB hash that was originally introduced by Hubachek and Wicks in 2015. And they kind of use this notion of a Merkle hash. The reason why they did this is because it lends itself to, you know, an opening. You can imagine kind of like opening a path along a tree, et cetera, et cetera. But really, for our purposes, I want to jump ahead to assuming that, you know, we've added, you know, we use Rate-1 FHE, so we get Rate-1 and we get extractability. What we really now have, our last frowny face to turn upside down is fully local, and that's basically the big issue that we have. Don't have too much time to talk about it, but basically we need to build a SNARG for this language. What is the language that we want to build a SNARG for? Basically like hash, oh, the question, yes, yeah.
But what you just said is for Flex. He's thinking about the ordinary hashing that you verify after you open the SSB.
Yes, so in a regular SSB hash, you can just release the path of ciphertexts, and that's enough to open. Yes, because we just do everything deterministically. That's correct. So that's why, like, yeah, the original construction lends itself to like a kind of local opening in the sense of like, you know, you could give paths through m different tree for all the different indices, et cetera. But basically then what we have, so we want to build some SNARG for this language, which is saying, basically the language instances of this language are hash values, indices, and bits. So basically, you know, presuming we want to open the hash value h to the bit b on index I, and we want to prove that there exists some original string x such that when we hash x, we get the hash value h, and x on index I is bit b. Does this make sense for why this like would be a local opening? Because it's basically proving the fact that we could have, like, if we had some x that was b at index I, we would have gotten this hash value, and so we can. Okay, basically, yeah, there's some technical detail here that I'm not going to go into. We actually end up using a tool called a quasi-argument, which is a kind of like a weak weak proof of knowledge. And then we further modify the Rate-1 FHE from BDGM 19, just basically to make sure that we actually get these properties that we need of like local ciphertext compression. I can talk about that more like offline for anyone who's interested. Basically, the way that a quasi-argument works is that you can extract things like you can in a BARG. We can only extract like a small number of things at once, which is why we care about things being small. And so we're going to look at this whole computation and just like keep extracting a bunch of small things and then argue that this means that the overall computation is still correct. I know that was like super high level. I don't really, I think, have too much time to talk about it. Our theorem that we hopefully kind of given a little bit of intuition for so far is that we can build this flex hash under LWE. So to again zoom out and just revisit what is the overall trajectory we're doing here. Now we've successfully defined and constructed our Rate-1 flex hash. So the only thing left in terms of novel work to do is actually state our final theorem. So what do we want this construction to look like? In 3 words, the answer is basically hash and prove. This is a paradigm that was followed from the original work of Kalai and Panik in 2016 that defined RAM delegation, which we'll talk about in a second. But basically hash, as in we'll use our Rate-1 flex hash. We create a length of W plus polylambda bit hash H of all the witnesses. And then we're going to do some succinct proof that, basically all the witnesses are actually past the computation that we want. But this, how do we do this, right? This is kind of, I've put us back in the exact same problem that we started in and haven't actually made any progress. But, when we would have made progress, if we had some sort of weird SNARG that could be verified against just a hash of the inputs. Like suppose that pi was a SNARG that we can verify against X and H, as opposed to having to verify it against X and all of the W's, then maybe we would have made progress, because even though we only have polylambda bits left for pi, we don't need to send any other information. We can just send pi that's polylambda bits long, and the verifier can verify it against X1 through Xk and H. As it turns out, this magical object is basically a RAM SNARG, or the RAM SNARG is the closest that we can get to it. So I drew this picture before. In terms of SNARG constructions that we have, CJJ's SNARG for P is an example where the verifier has access to the entire input X. Obviously, in our holy grail, a SNARG for NP, the verifier has access to an input X, but not the witness W. And a RAM SNARG is kind of an in-between, where the verifier will have access to a digest of the input X. And so in all known RAM delegation constructions, this digest is just the Merkle hash. And so I think that's a helpful way to think about it, but really it's just any sort of, in terms of the definitions and what we require, it's just a collision resistant hash. And both this result is also from CJJ that we have RAM delegation scheme under LWE. So the important things here is just that because the verifier is verifying against a polylambda bit digest, the verifier runtime doesn't grow with the length of the input to the computation or the runtime of the machine verifying. It goes log with that, but not linear. Okay, so yes, there exists a RAM delegation component to LWE. In my last 5 minutes, I'm just going to try to give like the quickest idea behind the construction, which is our first try might be to just use this RAM SNARG, right? What if we just have pi be a RAM SNARG? And so we're going to verify it against a digest of all the instances and witnesses, and then have our SNARG. I'm using a little blue ribbon here to denote RAM proofs as opposed to our BARG proofs. This is not secure. Why? Because we can't contradict RAM soundness, right? If you think through like what we would actually try to do in the security proof, we need to produce an X and a W so that we can actually contradict soundness of the RAM SNARG, but we can't produce all of the W's, right? We can only extract one W from H, and so this is pretty much dead in the water. Of course, the thing we forgot was that we have this third ingredient, which is using CJJ to CBARG, and so basically we need to do the same thing, but actually do it K times. Because what we want is that we want to have this happening for each instance where we have a digest of Xi and Wi along with some RAM proof that they satisfy the relation. And then we're going to use our CBARG where the machine, basically the computation we're verifying is the verification of this RAM proof. This is an example of what I was talking about at the beginning of my talk, where we're going to basically construct proofs where the computation we want to verify is the verification of another computation. And here, basically, we're going to get the succinctness we want, assuming that these witnesses are short, right? Because now I've changed the problem into this is going to be, even with CJJ's multiplicative overhead, if the length of the witness itself is already just polylambda because it's a short digest and a short proof, then we're still good. So we can still get away with a succinct proof overall. This is also not secure. Basically, if all we have is these digests like living in the witnesses, and if we can extract like one Wi star from each, and then we extract the corresponding witness, so like the corresponding digest and RAM proof for Xi star and Wi star, we need to ensure that the W star that we extracted from H actually matches the digest that we have in the RAM proof. So this kind of has, I think, sort of come up a little bit a couple of times during the talk. It's very important in reality when we're using this flex hash to actually verify the correctness of the digest. Otherwise, we don't really get any of the guarantees we want from soundness. So the way that we do this, we actually are going to just blow up the number of instances. Instead of having just K instances, we're going to have K times the length of the witness instances. So we're going to have one instance for each bit of each witness. And then we're going to add these witnesses where we're going to add to them an opening for the digest, which is this path, and an opening for the flex hash, which is this row. And again, these are both going to be succinct because we're just opening one bit, and we have to do this basically across. Now we're going to have length of W times K instances, but we don't really care about that because that becomes a log factor. And the important thing is that each witness is actually still succinct because it just consists of a short digest, a short RAM proof, one bit of a witness, and then two openings. So the two different kinds of hashes. And what we really want is basically the point is that intuitively we're trying to ensure that the H and the digest correspond to the same W in memory. And that's why we're going to like provide both openings. And then, yeah, I don't think that it'll be super helpful to go through this, but basically like general outline of security proof, you try to basically extract the things that you want. So you're going to extract W star from H, and then extract, the digest and one of the RAM proofs, and you encounter a couple of cases. In the case where the digest does match, either if the proof doesn't accept, you can break the BARG extractability because the BARG is going to ensure that the proof should accept. Like that's one of the things that the BARG is checking. If it is a valid proof, you can actually break RAM soundness because now we have, this W star, and we know from the original condition that this is not actually going to pass M, which means that we've broken RAM soundness because we've produced the XI star and the WI star that we need in order to contradict RAM soundness here. This is the thing that we couldn't do before because we couldn't extract all of the W's, but we can extract one of the W's, so we can do it for one instance. The second case, which is that the digest doesn't match, then we need to do more. We need to start extracting those two openings that I talked about, either breaking BARG extractability if the openings aren't valid, or breaking the hash opening soundness, the flex hash opening soundness / extractability if it is a valid opening and we still don't have that the digest matches XI WI star. I realize this is super fast. Basically, the point is that we in all the different you have a different case for each of the different primitives, and in each case you like break one of the primitives based on the original thing. But I'm very happy to go into more detail and with questions or anything. There's quite a bit of oversimplification happening here. So for anyone who is like a little bit more in the literature, I'm very happy to also talk about like what we actually do and the way that this is like the main ideas, but not exactly what actually happens in our construction. Okay, yeah. Any questions or thoughts? Comments, concerns?
No questions.
Thank you for inviting me. Well, all of CMU, thank you for inviting me.
Yeah, you are always welcome to come. Give more thoughts.